Welcome back. In the last class, we covered principle of oscillations by considering a feedback system with loop gain A beta and phase shift by A beta 180 degrees and a negative feedback representation like plus or minus, which is what is giving extra 180 degrees. Then that is what is represented without input. Then let us say the loop gain is nothing but mod A beta and the loop phase shift is nothing but 0 degrees, right? If you consider the total loop gain, right? Sorry, the total loop phase shift mod A beta 180 and this is what is minus 1, which is what is plus minus what you represent. If there is no input, that plus is becoming, it is nothing simply whatever feedback you have, that is what is fed back with minus 1, which is nothing but minus 1, 180 degrees. The total loop phase shift is 0 degrees or multiple of 2 pi. That is what is giving you oscillations. If mod A beta or total loop gain, if that is what is greater than 1 over damped oscillations, means unstable output, less than 1 under damped oscillations, output will be 0 ultimately, is equal to 1 sustained oscillations. That is what is case 3b. Okay, write down principle of oscillations. Principle of oscillations. Principle of oscillations. Remember, if you want to go back, you can go back also. Whatever it may be, the total loop phase shift. Okay, write down case 1. Principle of oscillations. This is what is nothing but Barkhausen criteria. Okay, principle of oscillations are Barkhausen criteria. This is nothing but Barkhausen criteria. Write down, it is associated with 2 points. Okay, the first point is always primary, second point is secondary. Okay, write down the first point. The total loop phase shift. The total loop phase shift. I am speaking about loop phase shift, not A beta phase shift. Okay, the total loop phase shift. The total loop phase shift must be equal to 0 degrees or multiple of 2 pi. The total loop phase shift must be equal to 0 degrees or multiple of 2 pi. The total loop phase shift must be equal to 0 degrees or multiple of 2 pi to get oscillations. To get oscillations. The total loop phase shift must be equal to 0 degrees or multiple of 2 pi to get oscillations. To get oscillations. Dot. The frequency at which the total loop phase shift, the frequency at which the total loop phase shift is equal to 0 degrees or multiple of 2 pi. The total loop phase shift, the frequency at which the total loop phase shift is equal to 0 degrees or multiple of 2 pi. 0 degrees or multiple of 2 pi. 0 degrees or multiple of 2 pi, comma, it is called as resonant frequency F0. It is called as resonant frequency F0. It is called as resonant frequency F0. It is called as resonant frequency F0 or frequency of oscillations I hope everybody understood, right? The total loop phase shift must be equal to 0 degrees or multiple of 2 pi to get oscillations. The frequency at which this is what is satisfied, the loop phase shift is 0 degrees. That is what is your frequency of oscillation. Let us say this is giving 180 degrees, okay, I'm just interested for a frequency 1 kHz sine wave. Then this is giving 180 degrees. Let us say this is not giving 180 degrees at 1 kHz. It is giving 170 degrees. Then 170, 180, 350. Right? That frequency will not have positive feedback. That frequency will be died out. Only the frequency at which total loop phase shift is 0 degrees or multiple of 2 pi, that is what is having restoration or regeneration, or I can say positive feedback. Then the signal will be restored and then give you oscillation. An oscillation, that is what is our frequency of oscillation. Remember, okay? Maybe if you want, you can try whatever system I gave you right here. This is plus minus, which is giving 180 degrees. This is giving 180 degrees. Therefore, total loop phase shift is 0 degrees or multiple of 2 pi. That's why you got oscillations even though there is no input. Okay. Now, instead of 180 degrees, you take like some 120 degrees. Then, if you do it right, it is not so easy because 180 degrees is represented as -1. But how will you represent 120 degrees? We cannot represent like -1. We have to write like a sine wave. Sine wave, if you take it continuously, that sine wave at what frequency you get 170 degrees or 160 degrees or 120 degrees other than 180 degrees here, then that will be died out because there is no positive feedback. Okay. Therefore, only at a frequency the total loop phase shift is 0 degrees. That is what is frequency of oscillations. Once you get oscillations, whether you are getting sustained oscillations or over damped oscillations or under damped oscillations, that depends on loop gain. Okay. Now write down case 2 or point number 2. Point number 1 is nothing but total loop phase shift. Total loop phase shift. Don't write, you already wrote it. Total loop phase shift must be equal to 0 degrees or multiple of 2 pi. Multiple of 2 pi. That will give you, therefore this is what is going to give you at what frequency, therefore this is what is going to give you resonant frequency F0. Okay. Now case 2, write down the total loop gain, actually this is related to phase response, this is related to manual response. Total loop gain must be equal to unity. Total loop gain must be equal to unity to get sustained oscillations. To get sustained oscillations. Okay. To get sustained oscillations. But let me tell you, this is always primary, this is secondary. Let us say total loop gain is 1, but total loop phase shift is not 0 degrees, then we will not get oscillations. The frequency at which the total loop phase shift is 0, then you will get oscillations. Whether you get over damped, under damped, critically damped or sustained oscillations, that is what is depending on loop gain. I hope this is clear. Okay. Always the primary is phase shift, secondary is loop gain. Okay. First of all, we have to look for the condition, the circuit which is what is satisfying the condition of phase shift which is what is equal to 0. That is what is primary, and then secondary is nothing but the total loop gain must be equal to 1. That is what is going to give you sustained oscillations. Okay. Done. Now maybe you can write a note for case 2 only. Note, if loop gain is greater than 1, if total loop gain is greater than 1, if total loop gain is greater than 1, what you get? We will get over damped oscillations. If total loop gain less than 1, what do you get? Under damped oscillations. I think this is what I explained, right? This is nothing but case 1, A beta, mod A beta greater than 1. This is what is case 2, mod A beta less than 1. This is what is case 3, B. But here also case 1 B, case 2 B, but with input only I explain, but without input also if you do, maybe if you try like case 3 B, similarly case 1, case 2, you'll get same observation. Okay. I hope everyone understood, right? Now, therefore, now whatever may be the system without input. Therefore, if I convert this into like this, let us say this is what is my open loop gain A, and this is what is my beta network. Output is sampled and then fed back, and this is what is the input. If I speak about oscillations, whether I get oscillations here, doesn't matter for me. Okay. Then tell me, if this is what is the scenario, what is your loop gain? Loop gain is A beta. What is your loop phase shift? Whatever phase shift you are getting from A and whatever phase shift you are getting from beta, whatever may be the total loop phase shift must be equal to 0 degrees or multiple of 2 pi. Whether you have A beta combined or A beta separated, doesn't matter for us. That's why the principle of oscillations, if you see, the first point is total loop phase shift. Therefore, total loop phase shift. Now there is no input. Input is nothing but simply a noise or a coupling noise, whatever it may be. Therefore, the total loop phase shift must be equal to 0 degrees or multiple of 2 pi to get frequency of oscillations. Okay. Now, case 2, the total loop gain. Now, the total loop gain must be equal to unity to get oscillations, sustained oscillations. If that is greater than 1, overdamped, less than 1, underdamped oscillations. I hope it is clear, right? Just blindly follow these two, but always we consider the primary point, which is nothing but total loop phase shift, then secondary point, total loop gain. Okay. I hope this is clear. Now take it, then maybe you can write the same system, closed loop system, whatever you want you can write it, right? But you can use it. But remember, this technique can be used to define gain margin, phase margin, etc. That part I will explain. I'll explain now only. What is gain margin, phase margin? Using this I can explain. Okay. If you separate this out, let us say -1, then you should give 180 degrees, because this is giving 180, this should give 180. If you combine these two, A beta -1 or A beta, whatever may be, the total loop phase shift must be equal. If you include this -1 inside beta, that is what? This is 180. Let us say this is giving 180, it should give 180. If this is giving 0, it should give 0. 0 means 360 basically. 0 means 0 delay in time domain, but it could be like 360 degrees, it could be 720, that is also multiple of 2 pi, right? Whatever may be, therefore 0 degrees is nothing but 360 degrees delay or more than 360 or multiple of 2 pi. This is also 0 degrees or 360 degrees, okay? But mathematically 0 degree, 0 degree, 0 degree only. Doesn't matter, okay? Done. Now let's see the meaning of gain margin and phase margin with respect to the examples or with respect to the cases what I explained, okay? Everybody understood principle of oscillations, what I explained? These two, the 2 points what I explained, they are nothing but principle of oscillations. Now, I just explained before using root locus, one pole system, because that I explained with respect to Opamp, right? Because we did Opamp compensation to get stability, and we know that one pole system is always stable, two pole system is always stable, three pole system may be stable, may not be stable, four pole system may be stable, may not be stable. That depends on the K variation, right? Which is nothing but DC gain or low frequency gain, whatever it may be. Now, if you consider one pole system, one pole system, right? let us say G of S. What is G of S? Let us say K by S plus A. I already explained with respect to root locus. Let me explain with respect to polar plot, considering gain margin and phase margin. Okay. Now, don't write. Therefore, what is polar plot? Polar plot is associated with 0 degrees, minus 90 degrees, and minus 180, and minus 270. Right? This is what it is. Now, if you observe clearly, right? When K is varying from when K is varying from minimum to maximum, right? Then what is the value of G of S with respect to the frequency, right? With respect to frequency we want to have, right? Therefore, now tell me what is G of S if you have one pole, right? Always see, even though we are considering G of S, but we are analyzing for unity gain feedback system. You know, we are analyzing for the system. This is what is your G of S with unity gain feedback system. Actually, this is nothing but your loop gain A beta, I can say. And this is what is plus minus, and this is unity gain feedback system. This is your output, and this is what your input, right? Therefore, G of S is nothing but your A beta, or I can say loop gain. Already it is representing 180 degrees. Now, if it is having 180 degrees and the total loop gain greater than 1, gone. System is unstable. Okay, that is what it is basically. What it may be, let's see. Now, if you plot polar plot, how many poles are there? One pole. How many zeros? No zeros. It will always terminate at P minus Z into minus 90. What is P minus Z? P is 1, Z is 0, P minus Z. Therefore, it always terminates at P minus Z into minus 90. Therefore, here it is nothing but minus 90. Because P is equal to 1, Z is equal to 0. Therefore, it will start from something and then terminate at minus 90. This is what your polar plot. Therefore, now this is what is omega is equal to 0. When omega is equal to 0, and this is nothing but omega is equal to infinity. Therefore, from omega is equal to 0 to omega is equal to infinity, right? Maybe you'll have some confusion. This is what is omega is equal to infinity, right? This is what is going to what? This is what is going to, this is what is giving you what? This is what is minus 90 degrees, right? This is what? Therefore, here what is it indicating? We are taking G of S, gain and phase angle, right? When omega is equal to 0, then K by A. This is nothing but K by A. When omega is equal to something, root over A square plus omega square. As omega is increasing, your gain mod J of S will decrease. Therefore, the magnitude is decreasing. Slowly the magnitude will become 0. But the phase angle is becoming what? Now the phase angle is 0. Actually, this is what is the phase angle. Then this is the phase angle at omega is equal to 0. Now, as you change your omega, the phase angle is changing and then becoming finally 90 degrees at omega is equal to infinity. Whatever it may be, if you observe clearly, your G of S will not have 180 degrees phase shift for any frequency omega is equal to 0 to infinity, or for any value of K. For any value of K, and when omega is changing from 0 to infinity, your G of S will not have 180 degrees phase shift. If there is no 180 degrees phase shift, then definitely this is less than 180 degrees phase shift. This is 180 degrees phase shift. Total loop phase shift is not 0. Then you will not see positive feedback. Therefore, always the signal whatever you have, whether A beta greater than 1, less than 1 or is equal to 1, remember, or the loop gain greater than 1 or less than 1 or equal to 1, doesn't matter, system is always stable. You will get stable output or bounded output. That is what is with respect to one pole system. Now, if you consider two pole system, therefore, if you consider two pole of G of S, therefore, let us consider two pole system. If you consider two pole system, let us say G of S is equal to K by S plus A and S plus B, or you can say S plus P, S plus P1, S plus P2, anything is fine, right? S plus A into S plus B. Then now because I'll use, normally people use, right? That's fine. Okay, now tell me what is polar plot. Now if you see polar plot, this is 0 degrees, minus 90, minus 180, minus 270 and then 360. Ordered maybe. Now how many poles are there? We have 2 poles. How many zeros? Therefore P minus Z minus 90 degrees. Therefore P is 2, Z is 0, this is minus 180. It will finally terminate at 180 degrees at frequency is equal to infinity. Okay. Now if you ask me what is polar plot, it starts at 0 degrees and it terminates at 180. It terminates at 180 degrees with gain 0. With gain 0, right? Therefore, now if you ask me, this is what is omega is equal to 0 and now this is what is omega is equal to infinity, right? This is terminating at here. Therefore, what does it mean? When gain is omega is equal to 0, this is what is this, which is not k by what? A into B, that is what it is, right? Then omega is changing, the gain is changing and the phase is changing, but the maximum phase shift what you can get is 180 degrees, but at frequency infinity, then your gain is 0. We are getting phase shift 180, we are getting phase shift 180, right? Therefore tell me, this is giving 180 degrees phase shift, at what frequency? Infinity frequency, let us say. But what is the gain of the system? The gain of the system is 0. Then what is your loop gain? 0. Is it less than 1? Yes. Therefore, your output will be diode. Therefore, you will get bounded output. Even they are giving bounded input, you will get bounded output. That is what we are in case 2. Right? Now the phase shift is 180 degrees. But what is your mod A beta or what is your loop gain? Loop gain is 0. At what frequency you are getting phase shift of 180 degrees? Infinity frequency. Let us say infinity frequency. But what is the gain? Gain is equal to 0. Total loop gain is 0. Therefore, less than 1. It is what? Stable system. Your output is stable. Our output is bounded. Now case 3. Case 3. This is important. Case 3. Let us say 3-pole system. If you take 3-pole system, let us say G of S. G of S is equal to K by S plus A into S plus B into S plus C. Right? We have 3 poles. Now, if you have 3 poles, this is 0 degrees, minus 90 degrees, minus 180 and minus 270 and then minus 360. Okay. Now, how many poles are there? We have 3 poles. Therefore, it will terminate at P minus Z into minus 90 degrees. You will get P is 3, Z is 0. You will get minus 270. It will terminate at minus 270. Then if you ask me what is polar plot, the polar plot is nothing but this is what is polar plot. Omega is equal to 0. Here omega is infinity. Therefore, if you observe clearly, it is crossing 90, 180 and then going to 270. At frequency is equal to infinity, the phase shift is 270, minus 270. But whatever may be for non-zero frequency at a given frequency, this is omega 0, omega 1, omega 2, omega 3, omega 4, omega 5, omega 6, let us say something, we have 180 degrees phase shift. At non-zero frequency or in between 0 to infinity, it is crossing 180 degrees phase shift. At what frequency the phase shift is 180 degrees, this is 180 degrees, this is 180 degrees, therefore total phase shift is 360 degrees. We are getting a condition at non-zero frequency or in between 0 to infinity, then total loop phase shift is becoming 0 degrees. Now we need to calculate what is the gain. If this gain is greater than 1, because now the total loop phase shift at this frequency, this is nothing but your phase crossover frequency, the phase shift at which your systems, the frequency at which the system's phase shift is 180 degrees. Therefore, that is what is crossing your 180 degrees. This is what is our omega or omega phase crossover frequency. People call it as omega PC. At what frequency, right, it is crossing 180 degrees. That is what is your phase crossover frequency. It has phase crossover frequency, the system which is having 3 poles. Therefore, now tell me, at phase shift of 180 degrees, this is 180, total loop phase shift is 0 degrees. Now Barkhousен criteria first point is satisfied. At this frequency, it is having total loop phase shift is 0 degrees. Now we need to see what is the gain. Therefore, now we need to see what is the gain. Therefore, this is nothing but your gain. This is what is your gain. That gain is depending on K. That gain is depending upon K. Right? if you ask me K by, maybe at a given frequency which is omega Pc, K by root over A square plus omega Pc square, root over, that is what, right? Therefore S plus A j omega, if you calculate what is the magnitude, you'll get the magnitude. That gain is depending on the value of K. Not only A, B, C, it is depending on K also. Therefore only for some values of K, this gain will be less than 1. If gain is greater than 1, system is unstable. You understand the point? Therefore, that is what I told, right? The total loop phase shift is 0 degrees because this is what is 180 degrees at WPC and this is giving 180 degrees because plus minus, let us say there is no input, what it may be, our input is there. Now, tell me if total loop gain is greater than 1, system is unstable. Total loop gain less than 1, system is stable. Total loop gain is equal to 1, marginally stable. Principle of oscillations, that will give you oscillations, right? But with this I can say normal system stability also, right? Therefore this gain should be less than 1. Therefore that is the reason why always the reference, remember the reference is -1. What is minus? Indicating 180 degrees phase shift. 1 is indicating the gain. Therefore if the polar plot is crossing that -1, what does it mean? The gain is greater than 1 and phase shift of 180 degrees, system is unstable. I hope this is clear. Okay. Therefore, if gain is less than 1, system is stable. Therefore, if I summarize, at omega is equal to omega Pc, where G of S is providing 180 degrees phase shift, therefore total loop phase shift is 0 degrees or multiple of 2 pi, right? The gain should be, therefore if the gain magnitude, right, is less than 1, system is stable. If gain greater than 1, system is unstable. If gain is equal to 1, at what condition? At this condition, okay? If gain is equal to 1, marginally stable, this is what is going to give you oscillations. Marginally stable. This is what I explained. I explained 3 cases, right? Case 1, case 2, case 3. Write it, okay? Then I'll explain what is gain margin and what is phase margin, okay? That's fine. The same thing I can explain. See, in the case of polar plot, both magnitude and the phase shift is represented in one graph. Both magnitude and phase shift, both are represented in one graph. But if you take Bode plot, both are separated. Magnitude response and then phase response, both are separated. Okay. But ultimately, polar plot or Bode plot, both are same. Okay. That's fine. Done. I'll give you 30 more seconds. Try to complete faster. Then I'll explain what is gain margin and phase margin. I think almost done. I'll explain the definition of gain margin and the definition of phase margin. Okay. Remember, this gain is depending on K. When K is changing from 0 to infinity, definitely it crosses 1. Then your system is not stable. That's why 3-pole system may be stable, may not be stable. Let us say the realistic variation of K, where even though the realistic value of K taught from 0 to infinity, right? Then for the realistic changes of K, if the gain is less than 1, you can consider that as system is stable. But we should have some margins. What is that? Let me explain. Gain margin. Hope this is done. Okay. And from next lesson onwards, we will see the different types of oscillators, RC phase shift oscillator, etc. We have 4 types of oscillators. If those are all done, once you understand principle of oscillations, right, then they are straightforward, just mathematical analysis. That's it. The concept is important. Circuits are examples. Okay. Now, example. Let us say example. Let us consider this polar plot. Okay, the same system having 3-pole system. Therefore, I am considering 3-pole system. Are independent of anything, whether it is 3-pole system, 4-pole system, 5-pole system, doesn't matter. Ultimately, if I give you a polar plot, I am asking you, or I am defining what is gain margin. Okay. Now, if you take example 1, then if you consider the polar plot like this, right? This is 0 degrees and minus 90, minus 180 and minus 270. Okay. Just listen. Let us say this is what is having polar plot like this. Okay. And this is omega is equal to 0 and omega is equal to infinity. And let us say this is what is your minus 1 point. Okay. And let me say this is what is your gain. At WPC, this is nothing but your WPC, omega PC, phase crossover frequency. Let us say this is what is gain A. This is what is the gain, absolute magnitude, gain A. Don't say 1 by S plus A, that's why I told, right, that time S plus P1, but don't confuse, this is simply gain A, okay. Therefore, now tell me if A is greater than 1, therefore tell me if the gain A at what point? At phase crossover frequency, the frequency at which phase shift is 180 degrees, therefore total loop phase shift is 0 degrees, right? At phase crossover frequency, the gain A, if it is less than 1, in this case it is less than 1, therefore this is less than 1, then it is stable, then system is stable, right? Now example, let A less than 1 only, right? Let A is equal to 0.1. A is equal to 0.1. Therefore, tell me, when I say A is equal to 0.1, what do you mean by 0.1? Therefore, again, if I plot the polar plot, if A is equal to 0.1, right? Therefore, if I plot polar plot. This is omega is equal to 0 and omega is equal to infinity, right? And this is what is your minus 1, but this is nothing but your A, which is 0.1. Therefore, this is A but 0.1. Okay. Therefore, now tell me, this is nothing but 0 degrees, minus 90, minus 180 and minus 270. Okay. Therefore, now A is equal to 0.1. At what frequency? At omega PC, phase crossover frequency. Therefore, now tell me, if A is equal to 0.1, then tell me. Therefore, if A is equal to 0.1, then tell me what is gain margin. Gain margin is defined as tell me with what factor if you multiply, this is nothing but what? A, with what factor if you multiply the A, which is 0.1, therefore it crosses 1. Therefore gain margin is defined always with respect to 1. But A, don't add, let us say 0.1, therefore 0.9 if you add, therefore it will be 1. No, gain margin is not defined with respect to addition and all, it is always the factor. With what factor you multiply 0.1 such that it will cross 1 or it reaches 1. Tell me. Therefore, that is nothing but what? A is equal to 0.1. With what factor if you multiply, it reaches 1 or it crosses 1. That is nothing but 10, right? That is nothing but 10. Therefore, your gain margin is nothing but 10. The factor with which if you multiply A, it crosses 1. That is what is your gain margin. Now, this is what your gain margin. Actually, here itself I can explain. Therefore, this is nothing but your gain margin. Your gain margin is equal to 10. Now, let A is equal to 0.5. If A is equal to 0.5, what is gain margin? The factor with which if you multiply, it crosses 1. That is what your gain margin, right? Therefore, this is minus 270 degrees. Now, if you draw polar plot, let us say this is what your polar plot. Omega is equal to 0. Omega is infinity. Okay. Therefore, now this is nothing but your minus 1 point and omega PC. This is nothing but omega PC and this is nothing but 0.5. This is what your A, right? Now this is nothing but your A. Therefore, now tell me, this is 0.1. This is 0.1. Both are same. Okay. Therefore, now tell me what is gain margin here? The factor with which if you multiply 0.5 such that it crosses 1. Therefore, with what factor if you multiply it crosses 1? Can I say 2? Therefore, gain margin is 2 here. Which is having more gain margin? Can I say this is what is having more gain margin? What does it mean? Relatively, this is more stable than this. Because I told you this A is depending on what? The gain is depending on your K by something. Therefore, now even though K is varying for large variations, or let us say K is having more variations, we have more margin to cross 1. Therefore, we have large range of K such that it crosses 1. Therefore, we have more gain margin. But if we have gain margin 2, let us say we have taken some K range, but it is crossing the range what you expected. If it is crossing the range what you expected, it may cross 1 because we have gain margin 2. Therefore, this is relatively more stable than the system. Generic, what is gain margin? Therefore, generic, what is gain margin? Therefore, gain margin is defined as what? Gain margin is nothing but what? It is A. That is not gain margin. With what factor if you multiply A such that it crosses 1? For 0.1, 10. For 0.5, 2. If you observe clearly, 1 by A only. What is 1 by 0.1? If you multiply with 1 by 0.1, it will be 1. If you multiply with 1 by 0.5, it will be 1. That is the factor, right? Therefore, 1 by A, and where, remember, A is less than 1 for stable system. For stable system. Therefore, this is what is gain margin, which is always greater than 1. Then if I convert into dB, gain margin in dB, right, which is nothing but 20 log 1 by A, which is nothing but minus 20 log A. looks like this is negative, but remember A is negative. When A is negative, sorry, A is less than 1, log less than 1, negative, negative into negative, positive. Therefore, gain margin in dB, right? Gain margin in dB is positive for stable systems. Then tell me, for example, A is greater than 1. What do you mean by A is greater than 1? It is crossing 1. When it is crossing 1, definitely at phase shift of 180 degrees, if its gain is greater than 1, system is unstable. When gain is greater than 1, if A is greater than 1, then your gain margin is negative. Therefore, this is for unstable systems. Therefore, remember, your gain margin should be positive always for stable systems. The system which is having gain margin positive, that is stable. The system which is having gain margin negative, that is unstable. The system which is having gain margin is equal to 1. What does it mean? A beta is equal to 1, loop gain is equal to 1, sustained oscillations, that is nothing but marginally stable system. That is nothing but your principle of oscillations. Whatever I told, right? It should be positive. The system which has more gain margin, right, that is more relatively stable. It should be positive. Remember, this is also positive, this is also positive. Both are stable systems only. But relatively, which is more stable? This is more stable. The system which has more gain margin, that is what is more stable. Maybe I can comment on phase margin also. If you see gain margin here, let us say the frequency at which gain is equal to, the frequency at which gain, phase shift is 180 degrees, that is what is phase crossover frequency. That should be, at that frequency the gain should be less than 1. But remember, the gain will be greater than 1, less than 180 degrees phase shift. Let us say here the gain will be equal to 1, but here at this frequency gain is less than 1, which we need for stable systems. Therefore, at what frequency gain is equal to 1, then if you see how much the phase shift is away from your 180 degrees, that is what is called phase margin. Indirectly, gain margin or phase margin, both are associated but looking in a different way. That's it. Therefore, if it is less than 180 degrees, then the gain will be equal to 1. The frequency at which gain is 1, and then phase shift, if you calculate, the phase shift should be away from 180 degrees. How much it is away from 180 degrees, that is what is your phase margin. Okay, that is the phase margin which you have with respect to 180 degrees. Okay, that is what it is. You can take it, the same thing I can explain with respect to Bode plot, right? Therefore, phase margin explanation is easier with respect to Bode plot. That's why people went to Bode plot, because we have polar plot, Bode plot, both are same, but polar plot is explaining both magnitude as well as phase in one graph, but Bode plot separated magnitude response and phase response. Okay, that part I will explain. I will take one example, two examples: stable system Bode plot, unstable system Bode plot. Then I'll explain what is gain margin, what is phase margin. Okay. But people always, because we measure gain in terms of dB, that's why positive means stable system, negative means unstable system, right? But the system which has more gain margin, that is more relatively stable. But if it is positive in any condition, let us say, if it is positive, that is stable. You can take it as stable system. Therefore, 3-pole system, 4-pole system, 5-pole system, you take any number of poles, the system will be stable for few values of k. For few values of k. If for all values of k, if you take, definitely system won't be stable, because it crosses 1 for all values of k, for few values of k. In that case, practically people consider the practical variation of that k or DC gain or whatever you have, right? If the practical variation of k, if you take across PVT process various process voltage, temperature, and then variations from the process fab voltage due to power supply, temperature that is due to ambient nature or power dissipation from your IC. Remember, the K is varying such that if the gain is less than 1 at phase crossover frequency, the system is stable. Even though it is having 3 poles, 4 poles, 5 poles. Okay? But normally we use the term called always stable. 2-pole system is always stable. 1-pole system is always stable for any value of K. But 3-pole system may be stable, may not be stable. That depends on K. 4-pole system may be stable, may not be stable. That depends again K. Therefore, even though you have 10 poles, but which is dominant, that is what is important. Therefore, remember, out of so many, people make 1 or 2 poles dominant, then effectively it will be 1-pole system or 2-pole system or 3-pole system, let us say. But what it may be, if you calculate gain margin, right, for the practical variations of K, right, if it is having gain margin which is positive, you can say system is stable. Okay, but we should have some margin, because after fabrication, whatever expectation we had before fabrication, right, then the expectation of the modeling, if it is not correct and then you are getting more variation of K practically after silicon, then we may be entering into unstable scenario. That's why people try to have gain margin. Some margin we should have before fabrication. Okay, time is over for this session. Okay, we will continue in the next session. Then I'll consider a Bode plot, then I'll explain what is gain margin and phase margin. Okay, take it. We'll continue in the next session. Thank you.